Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the third in the series on design end-to-end. In the first video, I covered the process of defining the end product that we're looking to create. We saw it as the mysterious black box. There is a link to this video up in the corner if you didn't get a chance to see that one. In the second video, I peeled back the covers of the top level black box to reveal various function blocks that would implement this design. These are the smaller black boxes that make up the whole. We worked through defining what each one did in terms that would allow us to design what was actually inside them. We decided on how each of these function blocks interacted with one another. In other words, the interfaces between the black boxes. Now there's a link to this second video up in the corner if you missed that one. In this video, we're going to begin the process of actually designing the guts of these function blocks. I'm going to present our implementation options and introduce you to the tools that will help you come up with a working design. Now, my original goal was to cover the entire design in a single video. Well, after writing the script and then timing the whole thing out, I decided it was just simply too much to put in one video. Thus, I'm going to cover the input amplifiers and the output amplifiers in this video, and then the next video will cover the indicators and the power supply. At the end of this video, I will point out some really great resources that will help you in future projects, so stay tuned for that one. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. So our first stop is the input amplifiers function block. In the last video, we discovered that 3 identical function blocks existed inside the input amplifiers function block. Each of these provided the functionality required for an input channel of the mixer. Now let's remind ourselves of the required parameters for this design to meet our overall goals. First of all, the input impedance needs to be 10 k ohms or greater. Then the voltage gain or amplification factor needs to be 100 or plus 40 dB. The frequency response needs to be flat within 1.5 dB from 20 Hertz to 20 kilohertz. It needs to have a level control, needs to be able to operate off of a single supply. And then the output goes to 2 different clients, the output amplifiers and the indicators. Now, there are many ways I could use to accomplish these goals, but I'm going to choose to use operational amplifiers, also known as op-amps, because, well, they're really easy to design around, and it relieves me of a lot of the heavy lifting. Well, I'm not going to go into a detailed treatment of op-amp circuit design. For that, I will point you to the resources I will be presenting later on in this video. But the first question that we have to answer is one of overall circuit architecture. We need a total gain of 100. While we could do this all in a single amplification stage, when possible, it is a good idea to distribute gain across more than one amplification stage to help avoid instabilities. Now, I have decided to distribute this over 2 amplification stages. The first provides some isolation between the input from the outside world and the level control. It also presents our 10 k ohm input impedance. The second one completes the needed gain and provides a low output impedance to the output amplifiers. Well, the next question we need to answer is, to invert or not to invert? That is the question. We have 2 basic configurations for op-amp amplifiers, the inverting or the non-inverting. Now, from my perspective, inverting amplifiers are easier to design around when using a single supply. Furthermore, because I'm using two stages of amplification, the overall effect is non-inverting. The first stage inverts, and then the second stage reverses it. The basic circuit for one of these two stages looks like this. But we're going to be using a single supply, so we have to change this a little bit. Instead of connecting the positive input to ground, it is tied to what I call a pseudo-ground, which is really just a voltage supply at half of the power supply voltage. In a lot of cases, this is supplied using a simple resistive voltage divider whose output has a capacitor across it to make sure it is just DC. This is an AC ground, but a DC level. Now, I'm going to do this differently using another common and preferred method. I'll show this to you once I get to the power supply function block in the next video. But here's a hint. It's not a voltage regulator. At this point, we could just leave it like this and be done with it. However, as I have come to understand it, we want to keep the bias current the same for both the negative and the positive inputs of the op-amp if we want to keep it 100% totally happy and content. So, to do this, we change the circuit one more time. I'm going to add a resistor between the positive input of the op-amp and our pseudo ground. The value of this resistor is the same as the gain resistor associated with the negative input. Now we have to add the capacitors to our circuit. Well, we want to roll off the gain at some higher frequency to make sure we remain nice and stable and quiet. Among other things, we do not want our amplifier to be responding to any local radio stations or anything. So we always put a capacitor in parallel with the feedback resistor. The larger this value, the lower the frequency at which the gain rolls off. Now we also have to preserve the DC equilibrium of the op-amp from being disturbed by whatever input device we plug into this mixer. So we have to put a series capacitor between the input connector and the gain resistor. The value of this capacitor will affect the low frequency roll-off. The larger the value of this capacitor, the lower the frequency of our low frequency roll-off of the amplifier. Now, if we're going to meet our overall frequency response goals, we have to pay attention to the values of these two capacitors. Now we get to start the process of actually assigning values to these components. Well, I could sit down and pull out all of the equations for this circuit to derive all of the values of everything. In engineering school, we would create huge matrices of stuff and employ computers to do all of the math. Well, thankfully, we could use computers. But I chose a bit of a different method for simple stuff like this. So walk with me through my design process. The basic gain equation for an inverting amplifier looks like this. The voltage gain equals the value of the feedback resistor divided by the value of the gain resistor. I have two stages of gain here in my input amplifiers. My first step is to decide the division of gain to achieve a total gain of 100. Now the easiest might be for each gain stage to have a gain of 10. And I think that's what I'm going to aim for. Now the value of the gain resistor determines the input impedance of the amplifier. Our requirements tell us that this has to be at least 10 k ohms. So I'm going to make my gain resistor, 10 k ohms. With a gain of 10 and a gain resistor value of 10 k ohms, then the feedback resistor must be 100 k ohms to achieve this. Now, let's roll out my favorite simulation program, LTSPICE. I've put a link to the download site in the description for you. Well, here you can see that I've put all of the components with their known values into the model in LTSPICE. I've cascaded 2 identical amplification stages with the level control residing between them. So let's take a tour of the stuff I put in LTSPICE schematic, starting at the left and working to the right. First, we have the input source. Notice that it is a 25 millivolt signal at 1000 Hertz with the name AC space 1 period. Now, this name is required for the program to do our frequency response plot. And don't worry if you don't get it right, LTSPICE will kindly tell you that. We have our input capacitor, then the gain resistor, which we have determined to be 10 k ohms. We next come to the op-amp itself. Now you can see the feedback resistor is 100 k ohms with its parallel capacitor. Also, there is a resistor connecting the positive input to our pseudo ground. This one is the same as our gain resistor. The extra 100 ohm resistor helps to isolate all of the stages that use this pseudo ground. LTSPICE does not have a nice model for a potentiometer, so I used 2 resistors instead. I changed their values as needed to test the level control settings, with the total resistance of the 2 being 10 k ohms. Notice though that the level control does not reside between the output of the first stage and ground. Instead, it resides between the output of the first stage and our pseudo ground. The same DC level exists at the output of the first stage as does at the other end of the level control, so the overall DC current through the potentiometer is 0. But from an AC perspective, the pseudo ground acts as a signal ground to the signal passing through it. So the potentiometer operates as a level control without disturbing the DC equilibrium of the op-amp to follow. Because of this, there's no need to have a DC blocking capacitor between the 2 amplification stages. The second amplification stage is absolutely identical to the first in every way, so there's no need to talk about it again. Now comes the fun. We get to assign capacitor values. Well, I created a spreadsheet to help with the process of selecting capacitor values. This spreadsheet calculates the gain at 2 specific frequencies associated with our op-amp circuits. One of these is the reference gain at 1 kilohertz. This second is the target frequency. For the low end, this target frequency would be 20 hertz, and for the high end, the target frequency is 20 kilohertz. We put in the values of the gain resistor, the feedback resistor, and the flatness we want. The cells are highlighted when the gain drops below the required value. Now I've put a link to this spreadsheet in the description for you. Our target is 1.5 dB for both stages together. Now this gives us 0.75 dB per stage for 2 identical stages. Now looking at the feedback tab for the input amplifiers, we see that we start getting highlighted cells starting with the value around 35 picofarad. Now this does not mean that we choose a 33 picofarad capacitor, which by the way is the standard value, because the capacitor values have value tolerance and their values change with temperature. So let's stay away from that edge. How far back do we step from the edge? Well, I'm going to choose 27 picofarads because, well, this is 0.5 dB down and our goal is 0.75. If I choose a 10% capacitor and go with a COG type dielectric, then I will very handily avoid this precipice. Now let's consider the input capacitor. Going to the input tab, we can see the highlighting ends at a value of 1.9 microfarads. Like before, we're going to step away from this precipice. And like with the feedback capacitor, I'm going to choose a standard value which gives me close to 0.5 dB down. I will choose a 2.2 microfarad capacitor for the input capacitor. When selecting this, I will specify a 10% component. These don't exist in a COG, but the X7R is relatively stable temperature-wise. Now, I've updated my schematic in the simulation, so let's run our simulation to see the results. So what do they look like? Well, I have 39.5 dB gain at 20 Hertz. That's great. I have 38.8 dB at 20 kilohertz. That's also great. Both of these are above our 38.5 dB level. Further, the passband gain is at 40 dB, right where we want it as well. So we've achieved the desired frequency response per the simulation. Now we can turn our attention to the output amplifiers. Well, I'm going to use the same overall architecture for the output amplifiers that I did for the input amplifiers. The only real differences lay in the introduction of the mixing bus as well as the overall gain. Well, what do I mean by the mixing bus? Well, this is where the signals from the three inputs are added together. When we're talking about an inverting amplifier, such as what we're using here, it simply means that each input has its own gain resistor. Now, we could choose to have each of the inputs with a different overall gain in the output amplifiers. And to do this, we would just use different gain resistor values for each one of the inputs. But in our case, we want everything to be identical between them. So the gain resistors be the same value. Now, before we dive into the design, let's remind ourselves of the design parameters that we established in the last video. To begin with, the output impedance must be less than 100 ohms. We determined that the voltage gain or amplification factor needs to be 3.16 or plus 10 dB. The frequency response needs to be flat within 1.5 dB from 20 Hertz to 20 kilohertz. It needs to have a level control. It needs to be able to operate off of a single supply. And its output has two distinct clients. The first is the outside world, in other words, our output connectors. And the second is the indicator's function block. With all of this in mind, let's assign some component values. Well, we know from our specifications that our output amplifiers need to provide a total gain of 3.16. But we come down to the same question we did with the input amplifiers. How are we going to distribute this gain between the two amplifier stages? Well, I'm picking a number out of the air. I'll explain why in a moment. I think I'm going to keep the first stage with a gain of 1. With the first stage having a gain of 1, this means that the second stage will have a gain of 3.16 or thereabouts. Okay, so why did I choose the first stage to have a gain of 1? Well, with an overall gain of a mere 3.16, it's just plain easier. If we needed a lot more gain like we did with the input amplifiers, then I would have been tempted to do things differently. Now, let's assign some component values for our first stage. We can call this the mixing amplifier because, well, that's what it does. Like our input amplifiers, I'm going to use gain resistors of 10 k ohms. Okay, now you ask, why did he choose 10 k ohms? And that is a good question. It isn't because I somehow had a requirement to have a 10 k ohm input impedance like we did with the input amplifiers. This 10 k ohm is consistent with the design of the input amplifiers. Keeping a 10 k ohm input impedance to the mixing bus reduces the overall current required to drive signals around the thing. This in turn reduces heat generation within the device as well as the current demand on the power supply. So this is my starting place, my feel-good value. Because we're using a mixing bus, choosing 10 k ohms as the gain resistors means that we have 3 individual 10 k ohm gain resistors, one for each of the 3 input channels. With the voltage gain equal to the value of the feedback resistor divided by the gain resistor value and a voltage gain of 1, the feedback resistor and the gain resistors have the same value, 10 k ohms. We will use the same level control scenario as with the input amplifiers. The second stage will also sport a 10 k ohm gain resistor just like the first stage. This means that our feedback resistor wants to be 31.6 k ohms if we're going to achieve our gain of 10 dB or a voltage gain of 3.16. Well, it just so happens this is a standard resistor value for 1% resistors, and thousands of them are out there in stock at DigiKey. Now we get to choose our feedback capacitor value. Well, for this, I'm going to go back to my spreadsheet. Now I've created 2 additional sheets, one for the first stage and one for the second stage because, well, they're different than each other. Now I know the values of my gain and feedback resistors. These go in here as before. And looking down the list for the first stage, according to what I see here, I think 270 picofarads is my value. Moving over to the second stage and having put the gain and feedback resistor values in the spreadsheet, I move down the column. Here I think 100 picofarads is my value of choice. So let's put all of this in our simulation and see what we get. We get 10 dB of overall gain. Check. We get 8.83 dB of gain at 20 kilohertz. Well, this is above the 8.5 dB, so we are good to go. That means that we have the preliminary designs of the input amplifiers and the output amplifiers completed, so we can now turn our attention to selecting exactly which op-amp we will use. Well, because we're going to try to minimize the power supply voltage, while at the same time maximizing the output level, we want to use op-amps that have what's called rail-to-rail outputs. Oh, what does that mean? Op-amps without rail-to-rail outputs start to have distortion and even maybe flat topping well before they get to the power supply rails. So for instance, a TL042 with a 9-volt power supply may start distorting badly as it approaches 8 volts on the positive swing and down to 1 volt on the negative swing. But with rail-to-rail outputs, we get a lot closer to the power supply rails before we experience bad stuff. So I begin my search for an op-amp on DigiKey first with rail-to-rail outputs. Then I'm concerned with power supply requirements. A maximum power supply voltage, 12 volts to 50 volts. Then I go to the minimum supply voltage and I say, well, it needs to be able to tolerate 6 volts and below. And then I'm faced with the question, how many op-amps do I want in a single package? I have the choice of 1, 2, or 4. Now, if I use 4, then I only need 2 of these chips to do the whole mixer. That would be pretty cool. If, on the other hand, I chose 2, then there would be a nice discrete chip for each channel and 1 for the output. But then I'd need 4 of these chips to do it. Now let me think. Smaller, more compact. Let's go for the 4 op amps per package. And in the end, what I decided on is the ON Semiconductor NCV20074DR2G. Now, what does it look like? Well, let's see. Power supply voltage range, 2.7 to 36 volts. That's great. Worst case voltage swing is within 0.22 volts of the power supply rails, but typically it gets a lot closer than that. That's good. What about its output impedance? Now, we require an output impedance of 100 ohms or less. This chip's output impedance does not even approach 100 ohms until we get to about 150 kilohertz, and we're not going to be anywhere near that. At 20 kilohertz, it sits at about 15 ohms. So it will work perfectly for our application, which wants less than 100 ohms of impedance. And to add to all of this goodness, it comes in a nice 14-pin SOIC package, which is easy to solder by hand. And now the promised resources. I have found that this book, Op Amps for Everyone, originally published by Texas Instruments, to be an awesome resource when designing op amp circuits of nearly every kind. Now, it cannot be easily procured in book form anymore, but I did find a PDF of it on a college website. I downloaded it and provided a link to it in the description below. A second book, which is not directly related to just op-amp design, is this one, authored by Dan Pease from Linear Technology. It's called Troubleshooting Analog Circuits. There is valuable advice in there that also applies to op-amp design. There are copies available in various places. It is well worth every penny you choose to spend on one, and it's, well, entertaining reading besides. If you found this video helpful, please click on the like and don't forget to subscribe. Thank you so much for watching. Until next time, Toodle-Oots!